I've started recording. So, are there any questions or concerns from anything we have done so far, especially from the last lecture? So, we are in the midst of proving a very important theorem. And of course, I keep saying this with every new theorem, but perhaps the most non-trivial proof we have seen so far, which is only natural as the course progresses. You expect to see more and more non-trivial results, right? So the result we are trying to prove right now is Tutte's wheel theorem. And there are two viewpoints that I want you to keep in mind. And these are going to be especially useful when you're attempting the writing exercise 1, okay? Where you're going to use Tutte's wheel theorem to prove something else. You're going to understand the structure of graphs that are intercyclic, which means that any two cycles share a vertex, or simple graphs that are intercyclic. Okay, so the two viewpoints are, there's an induction viewpoint where you can take any three connected graph, simple graph, and you either remove an edge or contract an edge, and you get a smaller three connected simple graph. Okay, and you can keep doing this until your graph becomes a wheel. Okay. The generation viewpoint is for any three connected simple graph, you can start from one of the wheels, which is an infinite family. And from this wheel, which might have 10 vertices, 50 vertices, I don't know, you can construct your final graph G by always, at every step, you either add an edge between two non-adjacent vertices, or you expand the graph at a vertex of degree 4 or more, right? So at each step, you will have a simple three connected graph. And finally, at the end, you will get your desired graph G, okay? And that's basically what's written here, okay? So you have a sequence of graphs. The first graph is a wheel. The last graph is your desired graph. And everything else is as I said it, okay? So those are the two viewpoints. And in order to prove, it suffices to prove the induction viewpoint, which is that for any three connected simple graph, I can find an edge that can be deleted or contracted to maintain simpleness and three connectedness. Okay, unless your graph is a wheel. Okay, so we are trying to prove this result, right? This one with an arrow. Okay, and yesterday we saw a proof sketch of this, right? So I'm not going to go over everything we did yesterday, but there will be some amount of repetition because I wanted to make sure that I first deliver the intuition behind this proof, and then I give you the rigorous proof with all the necessary details. Okay. So let me just jump to what we are doing today, and I will come back to some parts from yesterday as necessary. So what is the plan for the proof? We are trying to prove by contradiction. Oh, actually, no, it's not a proof by contradiction, really. Depends on how you state it. Okay, it's not really a proof by contradiction. Sorry. Although you can think of it that way, but then you would have to write it differently. So it's actually what you call a direct proof. Right. So what we are going to do is we are going to assume that we have a simple three connected graph with the property that every edge of the graph is a bad edge. So for each edge E, neither G delete E nor G contract E is simple and three connected, right? And what we need to now show is that our graph is a wheel. So let me just put down the goal here. Goal is to show that G is a wheel. Okay, that is the only case in which all edges are bad edges. They cannot be deleted or contracted to maintain the two properties, three connected and simple. Okay. So I was thinking if we could somehow put steps to everything we are doing, because this kind of proof is quite common in graph theory. I don't know if you will be doing such proofs yourselves on the assignments very frequently or at all. I'm not too sure. Yeah, but not as non-trivial for sure, I think. Okay, so I want to make this proof a little bit more systematic so that in the future when you encounter such proofs, you are able to see that there is a pattern, that this proof falls into a standard pattern that many other results in structural graph theory fall into. Some of my own work has been very much inspired by Tutte's wheel theorem, which is perhaps why I'm so excited about it. Okay, so the main steps of the proof are as follows. The first step is to establish the existence of a certain structure, right? And the question is, what is that structure? Well, that you need to decide. Um, okay, so in our proof, the structure is what we call a partial K-wheel, which I defined yesterday. So let me remind you what a partial K-wheel is. And we established that our graph, under the assumptions we have made, has a partial one wheel. Okay, so that is what we did. That is one of the things we did yesterday. So what is a partial K-wheel? It is a path P. So look at this drawing here. It is a path P, V0, V1 up to Vk. You can call the edges E0, E1, E1, E2 up to Ek, right? There is a additional vertex which is not on this path. We call it the hub for reasons that will become very clear as you see the definition. So the hub is connected to every vertex on the path. That is the first property we want. We want all the internal vertices of the path, so V1 up to Vk minus 1, to be cubic vertices in the graph. Okay, so let me make them dark. So all of these darkened vertices, they are cubic vertices, okay, in the graph, which means all of their neighbors are already in the drawing that you see on the screen. Okay, the only neighbors that the only vertices that are not cubic necessarily, that are not necessarily cubic, are V0, Vk, and H. Okay, in this drawing. And we want the additional edge, that the last edge on the path is a contractible edge. This last edge is contractible. In the sense, what I mean by contractible in this lecture is that when I contract that edge, my graph is 3 connected. However, it will not be simple because we know that no edge has this property, right? So we want the last edge to be contractible in this sense. Okay. Are there any questions regarding the definition of a partial K-wheel? Is there anything that is not clear? Okay. Remember, our goal is to show that the whole graph is a wheel. So we are trying to get there. We are trying to show that there is a partial K-wheel in the graph, and soon we will show that actually the whole graph is more or less what you see. You need to add one more edge actually. Okay, so your graph is going to be a wheel. Okay, so what we did yesterday is we showed the existence of a partial one wheel. This was done. Okay, and let me quickly take you through how we got there, but I will not spell out each detail today. Okay, so let's just go there. We took an edge in the graph, which is contractible. We know that such an edge exists by lemma 9.11, by theorem 9.10, which says that there is always an edge you can contract and keep the graph 3 connected. The problem is you don't have simplicity or simpleness anymore, right? So the graph has multiple edges. So how can you contract an edge and get multiple edges? Well, we observed in this drawing here that the only way this can happen is if the edge you contract, let's say V0, V1, the two ends of the edge have a common neighbor. In other words, the edge belongs to a triangle or a 3-cycle. Okay, and so there has to be this situation. And now you look at this drawing, and this is nothing but a partial one wheel. You have a path with one edge. The hub H is connected to both ends of the path. And the last edge of the path, which is the only edge of the path, is a contractible edge. You contract it and the graph is 3 connected, right? So already at this point, we have established the existence of a partial one wheel, right? And that is the end of step 1. Now, step 2, yesterday I tried to go further and I showed you that there is a partial two-wheel in the graph, although that is not actually necessary in the proof. I just wanted to give you intuition, right? So we don't need to actually show the existence of a partial two-wheel. We have shown the existence of a partial one-wheel, and now we are going to go to step 2. We are going to choose a maximum structure, such structure, and the structure in our case is a partial k-wheel. So we will choose a maximum partial k-wheel. So what do I mean by maximum in this context? I mean a partial k-wheel with as many vertices as possible, okay, which is the same as maximizing k, right? So we will choose a partial k-wheel j, capital J. So that is a subgraph of your graph. I like to use capital letters for subgraphs, GHJ. Okay, so we have the subgraph J, which is a partial k-wheel with as many vertices as possible. Okay, good. And now we want to go to step 3, which is to show that the graph has to belong to the special families in this theorem, or the special family. In our theorem, the special family is the wheels. So we want to show that our graph is nothing but a wheel, right? All right, so this is where we are heading now. We are going to show step 3. There is going to be some repetition here because I've already shown you some of the arguments yesterday for the case of one wheel and two wheel, but now we are going to deal. Can you hear me now?
Yes, yes.
Okay. Sorry. Apparently both my Ethernet and my data stopped working at the same time, but then I was able to get the data fixed. I don't know what happened. So there was quite some silence. Sorry about that. What was the last thing anyone heard me saying? Can you tell me, Girija, please? Girija, can you hear me? Okay. Anyone else? What was the last thing you heard me saying? Wow. Am I disconnected again?
No, sir, like you were talking about the maximum partial K wheel J.
Okay. Good. Okay. So had I already gotten to step 3 or was I still at step 2?
So I'm not sure.
Okay. All right. So anyways, we have lost some time. Let's get back to, so we step 2 is we are choosing a partial k wheel j with as many vertices as possible, right? Okay. And we can do that because in step 1 we have already shown the existence of a partial one wheel. Okay. And now our goal is to show that the graph belongs to the special families in this theorem. So in our theorem, the special family is just the wheels, right? So we need to show that our graph is a wheel. Okay. So this is what we are going to do today. And there will be some repetition with yesterday's arguments.
So have you shared your screen?
Okay. Thank you. I need to do that. All right. So now I have shared the screen. Okay. Okay, so we are going to do step 3 today, and there is going to be some amount of repetition. So let's go. All right. So I need to. Okay. So yeah. So let us look at the edge, the last edge in our partial k wheel. Okay. So by this I mean let us look at this edge HVK, the edge joining the hub to the last vertex on the path. Consider the edge HVK. Okay. Clearly, if you delete this edge, your graph is simple. If you delete any edge, your graph is simple because the whole graph is simple. That means that when you delete this edge, the graph should not be 3 connected. right? Since G minus HVK is simple, it cannot be 3 connected. Okay? All right. So what do we know about deleting an edge in a 3 connected graph and the resulting graph not being 3 connected? Right? Yeah. Well, that means that our graph, after deleting this edge, we have a 2 vertex cut, right? That's clear. There is nothing non-trivial in this. So G minus HVK has a 2 vertex cut. Right? It could also be a 1 vertex cut, but that is do it yourself. What if there is a 1 vertex cut? Okay, I won't care about that. Okay, so let's make a drawing. How do you get a 2 vertex cut after deleting one edge? Okay, so let us say there are these 2 components. So let's call this 2 vertex cut S. Okay. All right. Now, where is the edge that we deleted? This is repetition from yesterday. The edge has to go between 2 distinct components. Otherwise, S would be a 2 vertex cut in the graph G. So the only possibility is that H is here and VK is here. Okay. Now H and VK, they have a common neighbor. If you go back to our drawing of the partial K wheel, H and VK have a common neighbor, VK minus 1. So where is that common neighbor? Well, it has to be in the set S, right? The only way they can have a common neighbor is if that common neighbor belongs to the set S. So VK minus 1 is here. Okay. There is another vertex here. Let us call this dude U. Okay. So VK minus 1 belongs to S. And let U denote the other vertex in S. Okay, good. Now I want to ask the following question. I want you to observe this edge, VK minus 1 VK, which is our edge EK, right? So I want you to look at this edge EK. We know that this edge is a contractible edge, right? VK minus 1 VK is basically the edge EK. Okay, we know that EK, when you contract it, you get a 3 connected graph that is not simple, right? We know that G contract EK is 3 connected. How is this possible? This is again something we did yesterday in a more specialized setting where K was equal to 1, I think. Okay, but now we are doing for the general K. It's the same argument. So why is this graph? How can this graph be 3 connected? You see, if you contract this edge, VK minus 1 VK, if you contract this edge, you get this contraction vertex, and the rest of the graph remains more or less the same, right? What will happen is H will now go to this contraction vertex 2 times because both edges are going to 2 ends of the edge EK. And everything here, so this is everything, it's the same stuff except VK. All of these vertices, they will be connected to these 2 vertices. But this is the graph G contract EK. And I see a 2 vertex cut here.
unless this is the empty set. If this is the empty set, then this is not a two vertex cut. And we know the graph is 3 connected after contracting the edge ek. So that has to be the empty set. In other words, this guy is a component by itself. So this must be empty. And that implies, because of the fact that G contract ek is 3 connected, and this implies that Vk is an isolated vertex. In other words, it's a component by itself. In the graph, G, after deleting the edge HVK and the two vertex cut S. Okay, so let us redraw this graph. Let us redraw this graph with the new information. So I have a set S. It's got Vk minus 1. It has gotten U. And here I have a single vertex Vk. And here I have a component which contains the vertex H. Okay? And Vk's neighbors are Vk minus 1, H, and, well, it's a 3 connected graph. So every vertex has at least 3 neighbors. And the only way that's possible is Vk is also adjacent to this dude. Okay? Vku is an edge of the graph. All right? And this is our edge Ek. So now I want to go back to our partial K wheel. So let's draw the partial K wheel here. Actually, why am I leaving so much space? Okay. Am I clearly audible? Is the quality good?
Yes.
Okay, thank you. Are there any questions at this point? Please feel free to ask them while I make this drawing. Okay, so this is V0, V1, V2, Vk minus 1, Vk. This is the edge Ek. All these vertices are cubic. Okay. And we found a neighbor of Vk called U. Okay. Again, this drawing is slightly misleading. Let me make a correction here to indicate this possibility. So U could be already in the drawing we have made. U can already be one of the vertices in this drawing. Can someone tell me, can U be any of the vertices from V1 to Vk minus 1? Can U be any of the vertices from V1 to Vk minus 1? No, because V1 to Vk minus 1 are cubic vertices. They are degree 3 vertices. Their neighbors have all been discovered. So U cannot be one of them because Vk cannot be adjacent to any of those vertices except for Vk minus 1, which is already adjacent to Vk, right? So U is not any of those vertices. U can also not be the same as H because our graph is simple. So the only possibility is U could be V0. Okay? So that is a possibility we need to consider. And the other possibility is that U is not in this drawing. It's a brand new vertex, which is not in our subgraph J. Right? J is our partial K wheel. Good. All right. Okay. So what else? What else? What else? Oh yeah, there is one more information here. By this drawing, we also know that Vk is a cubic vertex. So now we know that Vk is also a cubic vertex, degree 3. So let's make it dark. Let's darken it. Okay, so we have one more cubic vertex. You kind of see where this is going. We want to get a bigger partial K wheel. And that will be a contradiction because we chose the biggest partial K wheel. Right? Okay. Okay. So now let us first consider the case where u is not equal to v0. Okay. So now we are going to look at cases. Case 1, u is not equal to v0. Okay, good. All right. So let me make changes to the same drawing instead of making a new drawing again. So let's suppose for the time being that u is a brand new vertex. Okay. Now I want to look at this last edge here. Let's consider this edge. Vk to u. Okay. So again, this is something we did yesterday. So there's a claim which is that G contract UVK is 3 connected. Actually, you know what? Since I already did a special case of this yesterday, I am not going to prove this again. So do it yourself. And if you want a hint, look at yesterday's lecture. Okay. So we will prove that we have proved that G contract UVK is a 3 connected graph. Okay. So we know that this edge, when you contract it, keeps the graph 3 connected. That means that the graph after contracting this edge cannot be simple, right? So we prove the claim, and then that implies that the graph after contracting this edge is not simple. Okay, good. But what does that mean? If you can contract an edge and maintain 3 connectivity, but you lose simpleness, how is it possible? It means that the two ends of this edge, they have a common neighbor. The edge belongs to a triangle, right? So u and vk must have a common neighbor. Right? Okay. So now, who is that common neighbor? Either it is the vertex h, because vk's neighbors are already known to us. It's u, vk minus 1, and h. So for u and vk to have a common neighbor, it has to be either the vertex h or the vertex vk minus 1. How can u and vk minus 1 be adjacent? Can someone tell me? What does it mean for u and vk minus 1 to be adjacent?
So that's not
Either
possible.
it's not possible. It actually is possible, but then k is equal to something.
Okay, k equal to 0.
K equal to 1. K minus 1 equal to 0. Right? We already know that k is at least 1, but but when k is equal to 1, vk minus 1 will be v0. And in this case, u and v0 could be adjacent. But u cannot be adjacent to any of the other v1, v2, v3 because those are already cubic vertices, right? So this is possible if and only if k is equal to 1. Okay, and that is something we did again yesterday. So this case was done yesterday. And what happens in this case is that you can show that the graph has a partial two wheel. Okay, So what I would suggest to you is that you do it yourself in case you were not there in yesterday's lecture. So try it yourself. You basically need to redraw the graph and try to get a bigger partial wheel than the one you have. So you want to get a partial 2 wheel instead of the partial 1 wheel. The graph and find a partial 2 wheel. Okay, and that will be a contradiction because we took the biggest partial k wheel. So if your k is equal to 1, so you had a partial 1 wheel, then finding a partial 2 wheel is a contradiction. Okay, so this gives you a contradiction. Okay, so now let's go to the what is actually the easier case, when u and h are adjacent. Okay, so now let's make this drawing. So what happens if u and h are adjacent? Does anybody see a contradiction now?
Yeah, maximality of
Exactly.
capital G.
Once again, you have a partial k plus 1 wheel, which contradicts that you chose a partial k wheel with maximum number of vertices, right? So now this drawing that you see here is a partial k plus 1 wheel. Right? Why? Let's look at all the properties. Let's not fool ourselves by the drawing. So let's look at all the properties. We want all the vertices of the path to be adjacent to the hub, right? So that is clear here. All the vertices on the path, including the vertex u, which is on the path now, which is a new path, they are all adjacent to the hub. We want all the internal vertices of the path to be cubic, and we have already established that the vertex vk is cubic, so that property also holds. And finally, we want the last edge to be contractible, so that is vku, and we have already proved the claim that g contract u vk is 3 connected, right? So we are done. We have a partial k plus 1 wheel, and that is a contradiction. So now in this case, note that j union, so I'll take the original subgraph, union 2 edges, vku and hu. vku and hu is a partial k plus 1 wheel, and that is a contradiction again. So in both cases, in both possibilities, you got a contradiction, right? And so case 1 culminates in a contradiction. So now let's go to case 2, and this is where we will find the wheel, right? So now u is equal to v0. Okay, let's not jump to the conclusion that the graph is a wheel. I know some of you may want to. We need a small argument to jump to that conclusion. So let's draw the picture. v1, v2, v3, vk minus 1, vk. Okay, you've got the hub h. And what are the cubic vertices? We know this guy is cubic, this guy is cubic, these guys are cubic. We also know that the last vertex is cubic. And we know that this edge, vku, because u is equal to v0. Oh, wait a second, I made a small mistake. Okay, let me start with v0. v0, v1, v2. Okay, and we know that there is an edge here because u is equal to v0. Okay, this looks like a wheel, but is this the whole graph? Why can't the graph have more things, more vertices? So this is a question. Why can G not have any more vertices? So this is our graph that we have discovered so far, but this is a subgraph of the graph, right? Why is this the whole graph? Can anyone complete the argument? Supposing there is another vertex out there in the wild that we haven't discovered yet. What is the contradiction in that case? I want somebody to complete this. Why can't there be a vertex somewhere out there?
So let's say there's a vertex X that is outside of this, and we know that it must have three disjoint paths with VI,
Uh-huh.
where EI is one of the cubic vertices, VI.
Okay. Okay.
So then we can see that two of those paths must pass through H, because like two of the paths have to come from the right, because
Okay.
like right, it's just an intuitive argument.
Right. Right.
So yeah, we can't have that.
So in essence, you are saying that if there is another vertex, then the graph is not three connected. Is that what you're saying?
Yeah.
Right. Right. So we are going to use the three connectivity. Rather than using paths, I would like someone to point out a two vertex cut. So now can you think about cuts instead of paths and see if you see a two vertex cut in this drawing, if there is any other vertex. So let me put part of your argument. Suppose there exists a X that is a vertex of the graph that is not in J, the subgraph that we chose, or all the vertices that you see here. Then now can someone give me a two vertex cut? That turns out to be a more direct argument. Can you see a two vertex cut?
So we can remove the two non-cubic vertices.
Yes, V0 and H. So look at these two vertices. They are not cubic. So that means that this X dude, the only people he can connect to is V0 and H. X cannot connect to any other vertex that is already in the drawing because they are all cubic vertices. You already see all of their neighbors. Okay? So, since all vertices in Vj except perhaps V0 and H are cubic, I claim that V0H is a two vertex cut. This should be easy to see, right? And that is a contradiction because our graph is three connected. Right? So that means that, so we have proved this claim that these are all the vertices in the graph. And now because all the vertices are cubic, you also cannot have any more edges. Right? So all of the edges that are in the drawing are all of the edges you see. And now it is clear that G is indeed a wheel. Or if you like, a K wheel. Let me see. Yeah. 0 to K, that is actually a K plus 1 wheel going by the graph theory. Yeah, let me not write that. Okay, doesn't matter. It is a wheel. That's all that we care about. Okay. So this is it. This is the proof. Any questions or concerns? Any part of the proof that is not clear? Right? So let's just quickly take a look at all the three steps we did. We established the existence of a certain structure, a partial K wheel, where K is at least 1. We chose a maximum such structure. In some proofs in graph theory, you don't need maximum. Maximal may suffice. Um, okay, I don't know if that is true here. No, here you need maximum. Yeah, because of a certain case. Yeah, so in this proof, you need maximum. Yeah, because of this case. Because of this case, I will leave it to you to do it yourself. Because of this, we require maximum instead of maximal. So that you can think about on your own. Because in all other cases, what we did is we took the current partial k wheel and we added things to it to make a bigger partial k plus 1 wheel. In this particular case, what happens is you have to change some things. Your H is no longer the hub. The hub is a different vertex. And that is why you need to choose a maximum k wheel in this proof. And maximal does not really work. Or if it does, you need to do some additional work, which we don't want to. Okay. So we choose a maximum structure. That is our step 2. And then from here on, we need some arguments to conclude that the entire graph is essentially the structure you see with some additional edges or vertices. And that is when you prove that your graph belongs to the special families, which is the wheels in this case. Okay, so this kind of proof appears a lot in structural graph theory. I don't know if you will be seeing other such proofs or at least as non-trivial proofs in this course further down the line. But if we do, then you will be able to see that structure repeat, or you might see it in our future courses in math or in theoretical computer science. Okay, good. So we have another 4 or 5 minutes remaining. I don't want to start plenarity, which is the next module. We will start that on Thursday. I just want to say a few words about the writing exercise. 1, right? So as I mentioned earlier, on the writing exercise, you may collaborate, and in fact, you may also submit jointly. I would actually encourage that you form teams of 2.
Hello.
Yeah, go
Hello.
ahead, Biplab. Yeah.
Sir, yesterday sir, I discussed with my the collaborator Sayantan Banerjee, and sir, we thought that sir, before the writing assignment, is there be any other assignment like the normal assignment? The deadline is 21.
Yeah.
We will submit by 4 the assignment 2. So
Right.
between 4 to 21, is there will be any assignment or not? That's why I'm asking.
No, but there might be a deadline very soon after 21st.
Okay, sir. That's
Yeah.
I'm asking.
Okay, so I haven't prepared a third assignment yet. So I think I will give you a third assignment only when we are about to complete plenarity. So that may take another 10 days from today. So if you calculate, then it will be 12th. And then I give you 10 days. So the minimum I expect is 22nd March. But I think it will be even later than that. So maybe it will be like 24th, 25th March.
Okay, that's I'm asking. Actually, sir, we are facing sir lots of I think busy schedule with doing all
Yeah.
this stuff.
Yeah, no, I totally understand. So there won't be any other deadlines between 4th and 21st March. Okay.
Yes, sir.
Thanks.
Thank you.
Good. So regarding the writing exercise 1, I encourage you to collaborate in groups of 2, not only for the ideas part, but actually for the writing part as well. So if there are 8 or 10 students, then I would encourage that there be 4 or 5 submissions, 1 per 2 students. But of course, if someone is willing to do it on their own completely, that is also fine. That is your choice. Okay. This exercise is sure there is a thinking part to it, which is also fairly non-trivial, but the writing part is at least as non-trivial as the thinking part is, right? So it will be really marked not just for mathematical correctness, but also for how well it's written, which is true for all assignments, because I think writing is really important. But in this one, I will be paying even more attention to the writing part. Okay, so what you need to do on this exercise is you need to characterize. There are 3 parts, but I'm focusing on part 2, which is the maximum marks. I think I've announced it as 35 out of 50 marks tentatively. So you need to characterize the three connected simple graphs that are odd, no, sorry, not odd, intercyclic. So, and intercyclic graphs means that you cannot find two vertex disjoint cycles. There do not exist two vertex disjoint cycles. In other words, if you take any two cycles in the graph, then they will share at least one vertex, possibly more, but at least one vertex has to be shared, right? So these graphs, you're calling them intercyclic, and you will be showing that all three connected simple graphs that are intercyclic belong to some special families, or there is some special graphs along with those families. Okay, so you can easily observe, and that is part of problem 1, to show that wheels are intercyclic. And then there is another family that you need to show that they are that's also intercyclic. And then part 2, you have to prove that those two families, along with two special graphs, they are all of the simple three connected intercyclic graphs. Okay. And then in part 3, you are going to answer the following question, that if a graph is intercyclic, intuitively, if your graph is intercyclic, you would expect that you can delete some number of vertices and make the graph acyclic, right? And you would expect that number to be small because there are no two vertex disjoint cycles. You would expect that by deleting a small number of vertices, you can make the graph acyclic or a forest. And it turns out that the right number here is 3. There is at most 3 vertices that you can delete, and the resulting graph will then be acyclic. There will be no cycles. Okay, so use this to prove that there exists a set of vertices that has size at most 3, and when you delete these vertices, the graph is acyclic. Here G is any intercyclic graph, not just 3 connected intercyclic simple graph. Okay, you might have the question, why are we dealing with simple graphs? Well, because often we don't care about graphs that are not simple. Another point is that if you answer this question for simple graphs, then you can also deduce the answer for all graphs by doing some additional work. Because if a graph is intercyclic, the underlying simple graph also has to be intercyclic, right? So once you know these graphs, you can then analyze how you can add multiple or parallel edges and loops to these graphs to maintain the intercyclic property. So in some sense, the harder question is to first get the simple intercyclic graphs. From there, you can go and look at all graphs, but we are not going to worry about that in the assignment. Okay. And what you want to do is, so this is the main part of the exercise, and you want to use Tutte's wheel theorem. If anybody sees another way to do it, I will be happy to hear about it. But the what is expected is to use Tutte's wheel theorem to characterize the intercyclic simple 3 connected graphs. Okay. So I'll stop here. And I'm here for another 5-7 minutes in case anybody has any questions or concerns. On Thursday, we will start the next module, planarity. And in planarity also, we will be seeing 3 connected graphs. So there will be a connection with what we have already done. Okay.
So we can ask
Yeah.
additional hints in assignment too. Can we ask?
Okay. You may contact me for sure. And if I feel that a certain question really calls for additional hints, I may make an announcement for it for everybody, right? So that I'm giving the same options to everyone. But yeah, in general, for all assignments, you can feel free to reach out to me and I will be willing to provide moderate hints. And when I think that something is really more non-trivial than I expected it to be, I will probably give the same option to everybody and include a small penalty for the same, right?
So, and additionally, like if there are, let's say that I'm doing subpart D and I've used the result of subpart C, but I am not able to prove subpart C. So will I get points for subpart D?
Um, okay, so in general, if you want to use a result from part B to prove part C, that's totally fine. You don't need to prove part B. You can just use that to prove part C. To use C in B, that is something I would be more cautious about. So in that case, you should check with me. So if you are using a previous part from any problem
So I'm not.
to prove a latter part, go for it.
I'm not saying that I'm just saying that let's say I've not been able to prove a subpart. Let's say it's A, but I want to
Okay,
use that result to prove subpart B.
that is
So
fine. That is fine.
so
So
I'll get
using A in B or 1A in 3B is totally fine.
even
But
if
using
I'm
3B in 1A, you should check with me.
but even if I'm not able to prove the
Yes,
previous.
yes, yes. Even if you are not able to prove, that's fine.
Okay. Thank
Yeah.
you.
Okay. Thanks. Okay. Any other questions or concerns? I'm the only one here. Okay. So let me stop recording.